Okay, 7 years ago, plosive, plosive, plosive. Did you, was that synced?
Sybilus. Syllabus.
Syllabus. Sally sells seashells by the seashore. Okay, is it working? Good, then we can start
Yeah.
our lessons. I did not write, I prepared the agenda, but I have not written it down on the iPad. So let me get that going. Share the iPad via cable. And also, let me go find my plan for today. Okay, so where is my wow, from this morning I got like 40 emails, so it's kind of hard to find. All right, so for the agenda today, there is review, as we always do. And okay, that had a bit of a lag. And then there's the questions about, what the hell, man? Are you getting the same lag as I'm seeing on my second computer?
There's always been a little bit of lag.
Yeah,
yeah.
Like, is the whole word just showing up, projects?
Yep.
Yeah, that's always been like that, though.
What is so friggin' hard about this application that it takes that? I've got like the most expensive MacBook you can imagine. And God damn, the more things improve, I've said this a million times, the more things improve, the worse they get. So. All right, and then floating point. Numbers. Let's see how those are put together. And okay, so let us begin with review. What would you like to review? Your review questions, things about assembly language, et cetera, et cetera. We'll get to questions about projects next. This is a review.
I don't know what to ask currently.
I got a good one. So in the last project, we had to check to see if a number is positive or negative. Is there a way that we can check, like, instead of comparing it to another number and then seeing if it's negative or whatever, is there a way we can read like the first bit to see if that's a negative sign?
Yes. There are a number of instructions that deal with testing bits. Okay, so if you turn to the ARM document where it was the big survey of all their instructions, you'll find them in there. So which bit would you test?
The first one, because that one holds if it's negative or not, or
Well,
holds its sign.
the first one meaning bit number 0 or bit number, N, 32 if it's bit 31 if it's a int, and bit 63 if it's a long.
Bit 0?
Wouldn't it be bit 63 or 31?
It's little endian by default.
Yeah.
We're not hearing you at the moment. No, like we cannot hear you. There are no words.
Thing 1, 2, 3.
We can hear you now.
Fucking Apple. Okay. How friggin' hard is it to get a Bluetooth working?
Very.
Right.
And that's why I just use a wire to connect mine to my headset to my laptop.
Well, with this fancy headset here, if you plug in the wire, you only get the headphones. You lose your mic.
Yeah, well, you have an actual microphone on my laptop.
Yeah. Yeah. All right. The more things improve, the worse they get.
That's just Apple, though.
No, it's everybody. It's everybody, because you know why? A lot of software coders out there didn't have me as a professor. So they don't give a shit about quality, and they don't know how to produce quality, right? They don't have professors like me who actually instill this need for pride, need for precision. And if you're just in it for the money, well, then you don't give a shit. You went to a 6-week boot camp, you don't give a shit. Let's move on to CompOrg, shall we? All right. So, Jordan, so I'm going to push back at you. If you did a compare and a branch, there's also a test a bit and branch. So it's also 2 instructions. So maybe in your investigation, you could consider whether or not there's an instruction available that will both test a bit and branch. Because then it would be 1 instruction. And at the end of the day, does it really matter? Okay. So comparing against 0, by the way, you don't have to load a 0 into a register. You have the 0 register, both W and X. So comparing against 0 is quick, real fast. Okay, other questions?
What is Malik's purpose? Because I was always grappling with that. Like I was using it, but I wasn't exactly sure what it was.
Have you used new?
In C++, yes.
Okay, so new calls Malik to get memory and then calls the constructor to initialize. So Malik is used to build new. So unlike new, Malik only gets memory, allocates memory, but it doesn't initialize anything. Okay. So new and Malik are both dynamically allocate memory from the heap. But new also calls a constructor's code. Okay, does that help?
Yeah, thank you. It's hard to do something when you don't know exactly what it means.
Yep, so Malik is malloc, memory allocation.
Were we not supposed to use the ABS function? I didn't really get that.
Well,
wanted us to use compare the actual bits. I just use ABS.
well, you can, but it's slower, right?
Probably, I don't know. I think.
Because you have to, calling a function could obliterate registers. Calling a function touches memory, right, to store and reload X30, for example. So calling abs is way slower than just testing the sign and testing a branch, a negate, if necessary.
Or just multiplying it by -1, so it becomes positive again.
Right. That's a way of doing it as well. And what I would add there is that I'd be worried about using multiply because of speed. But then I would be showing my age, right? Today's multiply is no slower than any other instruction. All the instructions run at the same speed, except for those that deal with memory. But in the old days, multiply would have been slower. Yeah?
Isn't divide still slow? Slower, anyway.
Yeah, well, divide's complicated. Implementing a divider is actually pretty complicated. So I don't know. I don't know the answer to that, Cephas. It is my belief that all instructions are running at the same speed that don't deal with memory.
If I'm not mistaken, people often recommend you like do a single division, like you divide, get an inverse, and then you use repeated multiplication, which saves division cycles because division is generally slower than pretty much everything else.
Yes. Now, does that make any sense to do if you're only dividing by that value once?
I don't.
No, because computing the reciprocal is a division, right? So, but if you have a denominator that you need to divide by a number of times, then yes, it may very well be faster to take its reciprocal and then use that as a multiply, multiply, multiply. Okay, so what we're talking about is A divided by B is the same thing as A times 1 over B. So if you have a value that you need to divide by over and over again, so it might very well be faster to take its reciprocal. Certainly, in the old days, that's exactly what you would do. But there'd be no performance benefit if you're only doing one division, because computing the reciprocal is a division. Reaching back into the depths of my mind, if you can pre-compute the division, in the old days, you'd want to pre-compute that division and store it as a global variable so that you could avoid.
It's happening again. We're no longer hearing you. We still cannot hear you.
Nobody can hear me.
Now we can hear you.
This is with the new and improved Mac operating system, by the way. All
Just
right.
because it's new doesn't mean it's been improved.
Yeah. All right, I'm changing microphones. All right, so you should hear me now with a little bit of a difference in sound quality.
I like
And
this
now
one.
I'm hearing a goddamn echo.
Echo.
We don't hear an echo.
I'm hearing an echo.
Mm.
I heard no things.
You hate what?
I heard no things.
All right, well, what I said is if you people are screwing with me, I'm giving you all Fs.
If I
Sorry,
was messing with
Ethan.
you, I'd be
With
laughing.
the act. Come on. We all know you're the one who's doing this. You just want to teach the class, don't you, Cephas?
You're on to me.
All right, let me try this again. You realize that everyone in the world who's teaching a class right now is going through the same thing on a Mac who just updated.
Yeah, that must suck.
Are they going to make an update patch for this update?
What?
Are they going to make an update patch for this update to fix this problem caused by this update?
No, they're gonna call it a friggin' innovation. All right, can you hear me now?
Probably.
Yes.
Mhm.
All right.
I'm
This
sorry,
is the
what
way
did you
it's
say?
have to be. What?
What?
Jordan. For you, F for you, F for you. Everybody gets an F. Okay,
Nah.
So worth it. That
No.
was so worth it.
yeah. All right, so questions? Anybody?
I guess it's kind of about project 2. I had issues with my insert at a location where it finds a spot and inserts at a location. So if you wanted to either show somebody who had a complete project and show their portion or show your own, just so I have a better understanding of what I did wrong.
What's the symptom?
I got pretty close to everything working, and then it infinite looped where the head is the tail, and I've rewrote my insert, my find spot, like where it finds the location where the node would be inserted, and and I've rewrote the insert malloc command twice since I got the issue last night, but I couldn't finish it in time. It just keeps infinite looping where the head is the tail.
Okay, I'm going to grant those that want it 1 day. Would that help anybody?
I mean, yeah, I'll work on it today.
Yes, yes, it will help. It will help a lot.
Okay, so if you've handed it in already, just hand it in again tomorrow.
Okay, then never mind. Don't show me answers.
Okay. Yeah, because if I show you an answer, then that's it. Nobody can submit
yeah.
anything.
Yeah, I know. Okay, thank you.
Okay. Any other questions about project 2?
Not necessarily one about project 2, but like another review question.
Yeah, go ahead.
Could you go over when and how to like back up registers and restore them?
Okay. Let me get my virtual machine going. Okay. So let's share the screen. Okay. All right. So if you use X19 to X29, okay, and always X30, if you call a function. If you use those registers, you must back up and restore. Okay, so that's the rule to remember. Rule number 2 to remember: 1, 2, all other registers may be blown up by calling a function.
And when you say blow up, you mean like overwritten and just disappear.
Correct, overwritten. So if you're using the other registers, then you can't count on them having their old value coming back from a function. However, X19 through 29, you can count on maintaining their value, because the rule is that if a function uses those registers, it must back them up and restore them.
If we call our own function, are x0 through x8 deleted by default or a priori, or can we, if we're calling our own function, bet that they aren't, perhaps in some random use case?
Yeah, if you're calling your own function, then you as the designer can guarantee that certain registers are not changed. But making use of that assumption means that you're not writing interchangeable standard code. But you can do it.
Like if you're just making local calls to functions that you implement, then you
If they're
can.
all yours,
Yes.
right. So if you personally wrote the function and you personally guarantee that you're perfectly aware of which registers are changing, then yes, but consider that you're writing non-standard code.
Assuming it's not to be distributed anywhere else, you ought to be Gucci, as it were.
Right.
Nice. Okay. I
Okay.
was wondering if like BL always deleted those or something.
No, BL is guaranteed to destroy X30. So that's why you have to back that up.
So every time you BL, do you have to back up and then restore X30?
No, not every time you BL. Let's take, for instance, main. In the beginning of main, you back up BL, and at the end of main, you restore, not back up BL, you back up X30, and then you restore X30. So in any function that you write that calls another function, at the beginning of your function, you back up X30. At the end of your function, you restore it. The only way that the return instruction will work correctly is if X30 has been saved and then restored. Okay, let's take a look. Let's say A calls B, right? So on entry, and something else calls A, of course. So in A, so save X30. And then there's a BL to B. And that's a shorthand for saying this is address X. Put X, the address of X, that's this label, in X30 branch to B. Okay. Now inside B's code, let's say B does nothing except return. Okay, so when a return is executed, a return is a shorthand for put X30 in the program counter and branch, which is a very wordy way of saying branch to the place specified by X30. Okay, is that right with the brackets? No, the brackets are not correct. There. There is an instruction, by the way, that would be BR. That's branch to a register. From an address, go fish an address out of that register and branch to it. Okay.
So if I'm just branching to something in my program and that the thing I'm branching to doesn't have a return value, I don't need to back up X30.
Now, if you're using BL to branch to something, then you've got to have the function that uses BL has to have X30 saved. The
Right.
function that you're calling, if it doesn't call any functions of its own, then you don't have to save X30 in that function.
So like if I save X30 at the start of main and then back it up at the end of main, in main, if I'm branching to like, say, another branch that's also in main, if that other branch doesn't call any other of its own functions, then like the first branch doesn't need to back up 30.
Okay, so branch, and branch greater than or equal to, or greater than, less than or equal to, less than, and equal. These don't impact X30. This does. Okay?
Okay.
So bopping around inside one function, that doesn't impact X30. But calling another function does impact X30. And calling another function is used with the BL. Oh, good, Nate. I'm glad you weren't frozen like that. Yeah. So, you know, with the great big mouth and then he was frozen. Yeah. Okay. All right. Then let's take a look at the next project. And stop the sharing. Stop with the sharing already. All right. So go here and here, projects, this would be P3. So you're implementing tail, a simplified version of tail. Okay. Now tail, in general, prints the last n lines of a file. Okay. So once again, I do need to get my virtual machine stuff running. And did that work? No, it doesn't. Wow, that's amazing. That, okay. Just crap is not working today.
Tamel.
Not my fault. Not my fault, damn it. Okay. And okay. All right, then I also need an editor. What's it called on this machine? Code. It's called code. All right, and open folder. Just got to find it. And then the stupid orderings. Oh, the only thing that's important to you is the last 7 days. Mac UI is so awful. Windows UI is so awful. Just
Which
give
UI
me-
do you like? That's a good question.
I haven't written it yet.
Ah,
Doesn't like anything. He just likes to complain.
Yeah.
I'm waiting. I really want you to write your own UI. So then when you're teaching one of the intro courses, you're like, all right, we're going to install this UI or something like that and just scare them all.
Yeah.
It's not like I'm not already scared because I have no idea what the heck I'm going to be doing for this project.
All right. So let me just see if it's this directory.
Our new project is to write a UI that is
Yeah.
annoying and a whole operating system.
Rating is based
Okay.
on it, how much he likes it.
Yeah,
Yeah.
no, that's exactly
Right. Okay, I'm almost there.
The only UI he likes is probably from like 30 years ago or something.
Windows XP.
He probably has very specific things that he wants that nobody else is going to put in unless he does it himself.
So
Well,
he's
the
expecting
general
us.
statement. The general statement is there's two kinds of code, right? There's the
Country
code that you write, that's perfect, and the code everyone else writes, that's shit. Okay? Total shit.
What if their code is better than yours?
That's never happened in the history of all programmers.
Are you sure?
Yeah. Okay, so. And now let me check. Good. All right, so I'm ready to show the screen again. Okay, so A dot out, and you have to give it a file name. Everybody see that? So A dot out, and you give it a file name. Let's say I can't give it the main.s because then you'd see the source code. So how about okay, so those are the last 10 lines of the file. Let me create, here is line 1, line 2, line 3, and let's try that. And A dot out and ooh. Okay, so if it's less than 10, you get what you get. But now let's make a file that's more than 10. Okay. Let's see what this does. Okay, so you got the last, I wonder why there's a blank line there. Does anybody know?
You accidentally pressed enter.
No, there's a blank line there because there is actually a blank line. All right, so let me get rid of that blank line, write it out, and run that again. So how many lines were printed? 2, 3, 4, 5, 6, 7, 8, 9, 10 in the line 11. So 10 lines were written. Okay, so it's always the last 10 lines unless the file is shorter than 10, in which case it's the last n. Okay? That's what the program does. Now, how you go about it, there are some requirements. Let's go here. Okay, so you're going to be implementing a circular buffer. And a circular buffer, buffers aren't really circular, it's how you manage the buffer. Let's try. Looking at a small circular buffer. Okay. So let's say your buffer had 4 items in it. So 1, 2, 3, 4, and I screwed up. Let's say it has 5 items in it, 0 through 4. Okay. In your program, these are going to be char stars. So these are pointers to char. Now in your program, there are 10. In this case, I drew 5.
Question?
Yeah?
So those 5 represent lines, and they would have char stars to what was on each line of the file?
Yes, I was just getting to that. Give me a moment and then let me know if I answered your question. In addition to these, to this circular buffer, you've got one statically sized buffer, really big. Let's call it 4096 characters. And this is a constant that you need to check against as you're reading a character. Now, every time you go to read a line, you would first do a mem set. You got to look that up. Okay, so mem set is going to reinitialize this static buffer. Instead of static, let me just call it intermediate buffer. Okay, so the purpose of memset is to fill all 4096 bytes with 0. Then write a function, a dedicated function that will process the input in the following way. It reads a character, one character using read. And it says, is this character a new line? No. Reads the next character. Is this a new line? No. Maybe that's a space. Is the next character, read one character. Is that a new line? And no, 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 no. And look, the last thing that was read was a new line. So you don't store the new line. Okay, you store the 0. So now it's null terminated. Actually, it was null terminated by virtue of the memset. So count up. 1, 2, 3, 4, 5, 6, 7 bytes, including the null. So that means you do a malloc of 7, and then a copy from the intermediate buffer to the newly allocated memory. And then you look here and you say, what is my current what is my current index in the circular buffer? Well, right now, so you'll have this notion of current index. The current index is 0. So you look at 0 and you notice it started out as 0, which means you can simply copy this pointer into there. You do the next line. And then your current index is now number 1. So you notice that that's a 0. So you can make that a pointer to the next line. Then this is a pointer to the next line. And this is a pointer to the next line. And this is a pointer to the next line that you've malloced after having gone through the intermediate buffer. Now comes the circular part. Your next index, if you incremented the previous value, it would be 5, but there is no 5 here. You have to wrap around. So it's like the mod, you can, it's like modulus. So wrapping around 5 gets you back to 0. You read in the next line normally, but then to insert it into the circular buffer, you notice that index 0 is non-zero. It's already pointing to something. So you have to free it and then update. So once the buffer has been full once, once the circular buffer has been full once and you've wrapped around, you have to free the previous contents that was there. Okay? So let's take a look at a circular buffer. And it's only got 3 items. This one's make it simpler. Okay, so you've been wrapping around. So maybe this is line 91, 92, and look, 93. right? It's circular, so you've wrapped around. You've got to, in your algorithm, identify that you start printing here, then this, finally that. Okay? It's a circular buffer. So you always have a an index, which is the index of the next entry in the circular buffer to overwrite. So in the beginning, you would, here's my 3, and they're all empty. They're empty, you know they're empty because they have zeros in them. Your current index is the next index to be overwritten. So it starts out as 0. You do your reading of a line into the intermediate buffer, check index 0. Notice that it's 0, so you don't have to do any freeing because it's already empty. So you get rid of that, and instead, this points now to a string. And this is updated to 1. So index number 1 is the next entry to be overwritten. You read a line, look at index 1, notice it's 0. So you don't have to free anything. Just update the pointer. And now this becomes 2. You read in your line, you look at index 2, notice it's already 0, so there's nothing extra to do except overwrite it with the pointer to a third. So this is line 1, line 2, line 3. Now this becomes what? Not 3, it becomes 0 again.
Hey, Professor, do you think I could show a quick demonstration for this bit? Because I wrote
Oh,
an
you wrote a little simulator, huh?
interactive simulator.
Yeah, all right, I'll go for it. But if I think it's crap, then you get an F.
Oh, can we not do that, Pod? I
Willing
think
to take that risk. On behalf of Cephas, I'm willing to take that risk for him.
Okay, go ahead, Cephas. You can show your screen now.
you will forgive my dogs that are trying to break through the floor. They're crazy. So how does one share a screen? Oh, this one. Is this it? Oh.
There's a friendly green button.
So can you see this?
Yep.
So I will add like W, A, B, C, D.
Well, how big is your buffer?
I only have an 8. It's like a super simple one. There are only 8 elements. So if I say print, oh no. Oh, did I?
F, 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 F.
F, oh, okay. So this right here, it looks more, I think, does Mac implement like the color arguments differently than Linux? Because these aren't the same.
It's possible. But if this isn't going well, then let's pull a plug on it.
Wait, so this one, the blue one, which looks more purple on this version, is going to say that's where read is currently at. And then all the way at the end, write is about to write to currently clean. Well, there's
Okay, keep going.
So if I do R, it's going to do A. And that's where it is. And if I print it again, it looks like it moved. So now read is currently there. And if I continue reading, it's going to go all the way to the end and then it'll stop because there's nothing more. And I can continue writing E, I don't know, E, F, G. I'm just putting random things in and eventually it should go to where we have overwritten these characters. See that?
Mm-hmm.
So the things that used to be in the first part have been overwritten, and now they're like, it's circular. So it just keeps on going around and will overwrite the new ones.
Okay.
We buy that? How do I get out of here?
All right. So I've,
Is that I did it correctly, right?
yeah.
I just failed.
Okay. So as, let me just do one more. So the index is wrapped around to 0. You read in your line, and you notice that 0 already has a value in it. So you have to free this. So free. That's all gone. And then you would write the next pointer. This is line 4. This is updated to 1. So, which is, and then you have the end of file. Where do you start writing from? Well, this would have been the next one overwritten. So it must be the oldest value. So you take that, reuse that current index, and you start at line 1. So index 1, so you'd print this, then, I'm sorry, you'd print this, then this, then this, and you're done.
So in our project, we're only going to store like 10 lines basically, and we're going to keep
Filter them
overwriting it.
through, right?
Yeah, until we end up needing to write or to print out the last 10 statements, and then we're going to be starting at like the oldest. Okay, all right.
That's exactly right. Jordan, you got that exactly right.
Also, I have a question. So what
Yeah.
I'm doing when I allocate a temporary buffer in which to read all the lines. So I'm like in a loop and waiting until read finds a new line or whatever. So as I find the new character, you put it inside some buffer of size 40, 96 or whatever buffer length, and then I deallocate that buffer. So I essentially create that buffer, copy it into the thing, and deallocate it and start the loop over.
No, you don't. You can just copy the bytes, right? So you have one buffer that is really long. It's the intermediate buffer, and you don't have to deallocate that. What you do have to do each time is call memset. Okay, so memset re-zeros the intermediate buffer.
So the
Okay.
intermediate buffer is going to be where we store each individual sentence, and then once we reach a null, the null terminator, we
New
basically
line.
the new line. Yeah, we have finished reading that, so then we save that to. Yeah.
Right.
And if the sentence is longer than 4096 chars, what do we do?
Okay. So let's say things that you want to use. You're going to have to use memset. You're going to have to use malloc. In the spec, is there a listing of other things that you're going to use? Yes. So
free Strelm puts and
yep,
printf.
strlen puts and maybe printf. Okay. And you also need free. Okay, and I don't think there's any problem in using strcpy. Okay. Now, Jordan, you finished. I wanted to write this down, but now I've forgotten the question I was going to answer for you.
Yes, what you
Oh,
do when
yes.
it's bigger than 4096.
Got it. So let's say your input line is 5,000 characters before it gets to a new line. Okay? then here's what you do. You've been counting the number of bytes. And at somewhere over here is 4095. That's one less than your buffer size. Right. So when you get here, you would copy this. Notice I go to the right of this vertical line. That's where your null terminator is. Okay. So copy all of this into your into newly allocated memory and have the pointer to it in the circular buffer. Then your read function just has to continue reading, ignore, 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 ignore until it hits the new line, and then it starts paying attention again.
Okay, and we don't store the new line buff, or we don't store the new line symbol.
Right. By not storing the new line symbols ever, then you could just use puts.
Yeah, and puts, just to confirm, puts will print everything up until the null terminator, correct?
Correct. And it adds a new line. It adds a new line.
Okay, I have another question.
Go ahead.
So I just allocated a buffer, did a malloc, then asked read to read a bunch of things and then change put all of that into that buffer. And then I set our thing in the tail length array, I guess, with the 10 elements. And then I added that as one of the entries in that tail array. And then I just reused the buffer again. You don't understand what I'm saying, do you? I didn't think I
No, I
explained
lost it at the end. If you have an intermediate buffer, copy the string out, right? So the string that you're copying out you're copying it out to newly allocated memory that's just the right size.
Okay.
Okay. Let's move on. You're going to need open and read. Now, these are the lowest level system calls for I/O. Of course, there would also be a write and a close. So make sure you close your file. Also, that's a requirement. Okay, so these are the lowest level input-output primitives on an operating system. So you got to look them up. The important thing is that open, some important things, returns a file descriptor. A file descriptor is a small integer. In fact, it is an index into an array of open files. This array is not in your address space. Okay, it's in address space associated with, the hell was that? Associated with your task, but you can't get at it directly. The operating system can get at it.
Can I ask a question?
Yeah, go ahead.
So this is just about creating the TXT file. Is it more advantageous for us to create it with VI in the virtual machine, or could we just create it inside our folder with our project as long as it's not in VS Code folder and it would do the same?
Yeah, it'll do the same thing as long as you have the SFTP copying it as it's
Okay.
being written. Right?
Okay.
Okay. Okay, so here is your open file table. Every process has one. Now there are 3 indices here that are special. And do you have any idea what they refer to?
No.
Is it the command line?
Now I use the C++ names. So by default, when a process starts up, there will be 3 entries in the open file table that are already representing open files. So file descriptor 0 refers to standard in is the proper name. So CIN is a higher level form of standard in. This is standard out, and this is standard error. Okay? So those are open files. If you want to read a character in the lowest level way possible, you would be reading from file descriptor 0 into some buffer. If you wanted to write to standard output, cout, it would be write to file descriptor 1. Okay, and this is true for all Unix-like operating systems. Okay.
So when you open the file, it's then assumed that this open file table, when you have a 0 for a read or a 1 for a write, is in reference to that one you opened.
Now, if you open a file, so here's a brand new program. So you have 0, 1, and 2 are by default present, and the rest of these are 0. They're nulls. When you open a file, the operating system will start at index 0 and march forward looking for the first available slot. So in this case, doing an open would get file descriptor 3. If you open 2 files at the same time, there would be file descriptor 3 and file descriptor 4. Let's say you close 3, which means this goes back to being a null. This is not a null. This goes back to being a null. If you were to do an open now, you'd get 3 again because it's the first available slot in the table. Okay, Nate?
Kind of. I just don't understand. So that read line there, you want to read from the CN into the buffer, but where does what the file you're opening and reading from come in? Because you're saying that it's stored at a different register in the table, you know?
Yep, here it comes.
Okay.
So you would be doing a read, not just a read of 0, but a read of whatever the open returned. Okay. Well, let's do a quick, yeah, go ahead.
So with the read and write, just to clarify, what is the second parameter? That's
where I was going right now.
Okay.
Okay, so here's open. And open returns, now this is the C version. Open returns the file descriptor. And the basic usage would be a C string for the name and then int for flags. And then you have to look up and see what the flags are. And here they are. Now, you're in assembly language though. So what's the value of ocreate? You got to look it up. Actually, you're not going to use ocreate. By the way, here's a piece of trivia. When Ken Thompson was asked, what would you do differently if you started writing Unix today? His answer was, I would have called it ocreate instead of ocreat. So it really is ocreat.
Is
Okay.
that the only thing he would have done differently?
Yep, that's what he said.
I would have made it O Canada.
Yeah. Okay.
I would have made it so you didn't feel like you needed a degree in order to read in the first place.
Well, I mean,
Okay, so here is read. The first argument is the file descriptor. That would be returned by open. The second argument is a char star. It's a pointer to a buffer. So, for example, you could keep the address of the next byte to be filled in your intermediate buffer. And then just keep incrementing. Of course, you're keeping a counter, right? To make sure you don't overflow the buffer. And then since you're reading one character at a time, that value would be 1.
If you set that count to like 2, would it read 2 at a time?
Yeah, it would read 2 at a time.
And what's the downside with that exactly?
Well, then you'll have to add additional logic in case that the first character you read was the new line, and then the second character was the first character of the next line.
Yeah, good point.
Right, so just read one character at a time.
so is there any reason why we're restricted to 10? Because I think it'd be pretty easy to make it more.
I originally, years ago, wrote this project with the mind of making it variable, but I made it 10 years later to simplify the project. Okay, now remember to pay attention. You've got errors, and you need to use p error, I think.
Yes,
P error, is that in the spec?
it is.
Yes. Okay. So any questions about the project?
How was this thing for the bubble sort? Some of us from the previous data structures class have not written one of these.
Bubble sort.
For the thing you need for us in the thing Cephas showed earlier.
Circular buffer?
Yes, we've
Circular
never written
buffer.
one before.
Yeah, so, right. None of you have written one before, probably.
I did a while ago.
Okay.
Okay.
So look, here is one more description of a, all in good time. Here's one more description of a circular buffer. Here's 1 to n minus 1, right? That's an array. Well, think about it like this. Here's 0, and here's n minus 1.
Okay, but if we're freeing 0, how will it know to go to 0, though?
If you're freeing 0, so you're saying that here is a char star pointer, and you want to free it,
Yes.
right? The reason why you want to free it, either it's the end of the program, in which case you have to free all of them, or you're overwriting the value. So you take this value and you free that value. And then overwrite it with the new value.
I was more asking, how does N1 remember the address for 0 when it has been freed?
I have no idea what that means.
You're not actually freeing the 0 like the buffer. You're freeing what's in 0.
Doesn't free get rid of everything inside that area, including where it points to next?
No, these are char stars. They're pointers. You're not removing the pointer. You're removing what the pointer points to. We can't hear you, Nate. You're muted.
Yeah, I know.
This is an array of char pointers. So when he's freeing this, you're only freeing the memory that the char pointer points to, not the char pointer itself.
Okay,
I thought
so
I was worried that we would have to make another type of struct for this, not just an array.
no, you have an array of 10 char stars. So if the, I'm just calling a table. So current is not equal to null. Free current table current. And then table current equals the newly alloced buffer. Okay, so if it is already in use, free it, then overwrite the entry. Okay, so current equals current plus 1. If current is equal to 10, current equals 0. There, I just looped around.
So some people do it like this. What's the problem with not just using modulo?
Not using what?
Modulo. Because that's how I did it. And
Is there even
What's-
is there a
what's
function
modulo?
like that in ARM? Is there
What?
even a way to do that?
Oh, that's fair. I suppose ARM doesn't have mod, does it?
Yeah, well, I've been wondering that the whole time. I'm like, I mean, I would totally use that, but I don't think that. That's
Like even in the C code, they implement it like this. Is there an advantage to doing it like this? Is mod expensive or something?
There's no ARM instruction for mod. So there you go.
That the only reason?
Yeah, so I showed it this way because there's no mod instruction on the ARM.
Okay.
It would take like 4 or 5 instructions. Yes. Okay. Let me show you how the ARM internally calculates mod. All right. You ready? So A mod B on the ARM would be A integer divided by B. That it does have. So let's see. 15 mod 3. So doing 15 integer divided by 3, let's call it 16 because I want to have a remainder, right? So that is equal to 5. True? Then 5 times 3 is equal to 15. Then finally, here comes the mod.
That's
16 minus 15 equals 1. That's how you implement mod.
That's a lot.
Okay, or you can have an if statement that wraps around.
Work smart, not hard.
Okay, but this is actually how it's implemented.
So there is a modular.
There's no single instruction.
Okay.
All right. Any questions about the project?
Do we just, I'm sure it's on the spec, but we just turn in the assembly code, or?
Yes, that's right.
How are we supposed to handle working as partners?
Okay, I told you only who you can work with. You cannot work with anyone else. Or you can work alone. So I have assigned partners. If you want to work with them, go ahead. Except in your case, Tom, where you are the odd man out, you can work with anybody you want.
Professor,
Yeah.
I just wanted to ask about how commenting is graded. I just want to briefly know like what you're looking for besides function headers with parameters and returns, or is that it?
Well, it's got to work correctly, and it also can't lose any memory. So that would be Valgrind. Let's go here, here.
Well, I know that the coding portion definitely is going to have Valgrind and make sure that nothing's lost and that it runs correctly. I'm just asking purely about comments. Like, is there a certain way that you would like us to comment besides what you provided here about description of the function?
Okay, so that's a function comment, and then you should also have comments embedded in the code.
Okay.
Now, you didn't have me for CS0 and 1 or 1 and 2. So what should you comment? You should comment, you should not comment what you're doing. You should be commenting why you're doing it.
Okay.
Okay, so for example, the example that I cite is I++ semicolon with a comment of increment I. Okay, you do that, then you just embarrass yourself, right? Because anybody who can read your code knows that what the statement did. I++ increments I. I don't want to see a comment like increment I. What would be more appropriate is, what are you thinking about? What is the purpose of incrementing I? That's what deserves to be commented, not the mechanics.
Cool.
Okay, so let's do Valgrind. And here's what I want to see. All heap blocks are freed, no leaks are possible. Okay, that is the only acceptable result. Okay.
So using Valgrind, we just supply the executable and the source code?
No, you don't need the source code. The .. /p1.s is the input.
Oh, okay.
That's the command line argument. Okay. All right, good. Let's, I'm still trying to figure out how to get the next thing that good, I've got it. The next thing to talk about is floating point numbers. And for this, I am going to shutter, perish the thought, utilize PowerPoint. Let's see, so here and here and here. Okay, this is online for you to follow. Let me share. And I get to show you another instance of improved software. You see that?
Beautiful.
Visual Basic for applications. I updated something from Adobe, and now I get this every time. And I have to get rid of it. How many times have I clicked?
23.
Took 4 clicks to get rid of it. That is
Hey.
pathetic.
Quick question about the groups for the project.
Yeah.
If our partner decides to work alone, do we get to choose what group if we want to work with a partner, or are we SOL?
You're SOL. Okay. So if we use partners again, it'll be some other black and white algorithm. So this time we used your email addresses alphabetically in every pair. Maybe I'll use if the email addresses using every third letter, the third letter as the alphabetized. Okay, let's talk about floating point. So you've got floating point registers. You got 32 X and Ws. Well, you've got 32 floating point registers also. They are 128 bits wide. So that's the equivalent of 2 double precision values. Okay, you can get at them using B for 8-bit, H for 16, S for 32, D for double, and Q for quad. So Q is, I should say, well, when you start looking at the neon instructions, the vector instructions, then you use a Q register, and you could be delineating it as 2 doubles or 4 single precision numbers. So you really do use all 128 bits once you start getting into neon. All right, so the floating point format used on the ARM is IEEE 754. IEEE is a standards body, so this is an international standard. So here is single precision. Single precision is 4 bytes or 32 bits. So floating point is divided, a floating point number is divided into 3 different regions in the bits. You have the sign bit, bit 31. And that sign bit determines whether or not the resulting number is positive or negative. If the sign bit is a 1, then the whole number is a negative number. Okay. The next group of bits, there are 8 of them. That is the exponent. And this is wrong. I fixed this. I fixed this. So, son of a bitch, I did fix that, but I don't know why it's not here. Maybe I didn't push. Okay. All right, now interestingly, the exponent is stored as a biased value. So an exponent of 0 is 127. So whatever number you've got there, we need to be able to represent positive and the negative exponents. But we're not going to tie up another sign bit, a sign bit for the exponent. Instead, whatever number you have there is offset by the value 127. Okay, so positive exponents you're all familiar with, but the way to get fractions is negative exponents. Okay, so looking at this screen, you have an exponent of 7c. So 7c minus 7f is in 2's complement. So you take the 2's complement of that and you get 3. So this is -3. So look at the math there. 7C minus 7F. That's a negative number. So this is a -3. Then you have a fraction. Now, the fraction is, you assume that there's a 1 in front of the fractional part. This is like a scientific notation. It is a scientific notation, but in base 2 rather than base 10. So here, can you see my, yes, you can. So this is the halved place. This is the quarters place. This is the eighths place, 16ths, 32nds, 64ths, and so on. So the value here is a quarter. So the number, the numeric equivalent here is 1.25. So this, interpreting this whole floating point number, it's 1 times, the 1 is the sign bit. It's either 1 or -1. So 1 times 2 to the -3 times 1.25. Okay?
I'm still confused in the exponent portion with the 7C and the 7F. I somewhat understand like the F's filling up that address, but I still don't really understand it.
Okay. So the exponent doesn't have its own sign bit. So we want to be able to represent both positive exponents and negative exponents. So the way that they do that is a clever hack where you offset the value that's there so that 0, the true value 0, is in the middle of the range. So 127 is 0. Less than 127 is a negative number. More than 127 is a positive number. Does that help?
Yeah, a little bit, yeah.
Okay.
I'm obviously going to look at it more, but yeah, that helps a little bit with understanding what's going on.
Okay. Now, there are 2 exponent values that are special. All zeros and all ones. All zeros and all ones mean infinity and not a number. So for example, divide by 0, you'll get not a number, NaN. So there are 2 values in the exponent area that are not normal, but they do come up when there's an error. All zeros, infinity, and all ones, not a number. Okay, so single precision will store from 10 to the -38 to 10 to the +38. That's a big, big range. Now let's look at double precision. This is ridiculous. From -308 to +308 as the exponent. So there's 11 bits, and the offset is 1024, and a 52-bit fraction. So where is the actual precision coming from? Not from the exponent. That gives you a range, a big, big range. The precision of the number is coming only from the fractional part. And in double precision, you have more bits of fraction. Now, as a digression, to give you some sense as to how big the maximum double precision number is, if you look at your screen and you can make out a single pixel on your screen, if you were to line single pixels against each other, pixel, 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 start with the center of the sun, there are enough values in a double precision number to link together pixels from the center of the sun all the way to Saturn. Okay? It's a really, really big number. Are floating point values exact?
Nope.
No, they're not. Floating point values are approximations. There are some numbers that can be represented exactly by floating point. Some numbers, no. Okay. Do we need to demo that? Okay, because I think in some CS1s, 1810s, I do it, but I'm not sure I do it all the time.
Isn't that like, oddly enough, I was talking about that in my data science course today, but like how 0 is never actually 0 on computers. Like if we're trying to
Well, it
say,
might be 0. 0 might be 0.
yeah, well, I mean, like if we're saying like, you know, is this number equal to 0, it's always like we have to find an error around 0.
It's not, but the only you're absolutely right, except for saying always. Right. So if you use the literal constant 0, it is in fact exactly 0. But if your 0, so to speak, in air quotes, is the result of a computation, it could be really, really, really close to 0, but not exactly. That's why, let me explain you something. Okay. So, Harry, calculation goes into, I don't know, something called altitude, right? If you write this, you die. Okay? You cannot do tests for equality with floating point numbers because they are approximations. The plane falls out of the sky. Well, if it's altitude 0, then, you know, you get the point. The way to properly test for equality with floating point numbers is the following.
Wait, don't you mean the thing you're trying to compare it to? Isn't it
Yes,
altitude
right.
minus thing is greater than
Right.
less
So
than?
altitude minus a value less than epsilon. So epsilon is a built-in constant into the math. You'll find it in cmath.h or cmath or math.h. And epsilon refers to the smallest representable value. So this is how you test for equality with floating point numbers without killing people. Okay, thank you for the correction, Cephas.
If we do want to kill someone, is that what we do?
You know, just like all things in computer science, it depends.
So in the second example, what would value represent in reference to the first example. Because, yeah,
Yeah,
okay, okay. Oh,
okay.
and then that EPSL is the smallest approximation that can be compared against another float. Okay,
Right.
that much makes sense.
Okay. So rule number one in going out into the field is don't write code that kills people. Right?
What if it's an endless rabbit hole?
You're in a rabbit hole?
If
Well, I
you,
could just start asking about conditions. Like, what if, I definitely want to kill this person? Like, what if he made a really, really bad UI that my awesome professor in college didn't like?
Well, these are hypotheticals and we are being recorded, Jordan. So why don't you shut up?
if you work for the military, you might want to write code that kills people.
Yeah. Okay. What is the next thing that I want to talk about? Oh, I think I still have some slides to go, though. Yes, I do. How to use floating point in ARM, assembly language. Okay. And here we are. We're back here. Okay, now floating point constants are not straightforward like they are on the left. Because think about it. All ARM instructions are 32 bits long. So how do you deal with a constant double precision number? The double precision number by itself is 64 bits long. Okay, so here is a single precision constant that the code on the right is the output of the compiler. This isn't how you or I would write this code. Instead, if it were you or I, we would make the literal a global variable. We know how to do that at the .data section. And we would move it from RAM into a floating point register. So what the compiler did was broke up this number, whoops, the 1.2345678, into its actual bits, put 32 bits worth into W0, and then loaded the upper half of W0, the part you don't usually get access to, right? So here, and it's covering up, this is a left logical shift of 16 bits. So this loaded 16 bits. Yeah, I said something wrong a moment ago. I'll say it again correctly. So here's the lower 16 bits, and here are the upper 16 bits of a 32-bit single precision number. And it's doing it 16 bits at a time because, remember, all ARM instructions are 32 bits long, so it can afford to do it 16 bits at a time, so it takes 2 instructions. So this is the lower order, 16 bits. This is the high order, 16 bits. I know that because it's a left shift by 16 bits. Move K is move keep. So this move instruction doesn't overwrite the previous contents. So if you look at W0 after the second instruction, the 1617 is still there. So move versus move keep. Then to go from the W register to the single precision register, F move.
So that move keep, when you're updating the upper half that's normally inaccessible of the W0, it also keeps the lower 32-bit half of the W0.
Yeah. See, that's the part I said wrong. That's exactly what I said. That was incorrect.
Okay.
So move keep, both of these instructions are confined to 32 bits. That's where I went wrong a moment ago, and I'm fixing it now. So both of these move instructions stay within the 32 bits of W0. But because the constant values have to be encoded in the instruction, they only have a certain number of bits available. That's why it's being done in two groups. Let me show you the next slide, which would be more like what you would use. So no, not this one, go here. Yeah, there we are. All right, so here's a return of a double precision. So take a look. Here is the bit pattern as a global variable. So there's 32 bits here. Damn it. There are 32 bits here. There's got to be a way to do this. Let's see, click that. And can I draw now? No. Come on, what's the story here?
Highlighter or pen, probably. Either
All
of
right,
those.
pen. So here's 32 bits, and here's 32 bits. Now, so this is output of the compiler again. If it was you or I working with floating point, then we wouldn't use the .word directive. We would use .double, and then we could put in .1.234.1.2345678 etc. So there's another assembler directive that you or I would use. The compiler just calculated what the bits were directly.
What is this shenaniganery over here? Hash colon LO12 colon dot LCO. What does that mean?
Okay, so that is these things are also generated by the compiler. It is computing the address of the LCO label.
But that doesn't even seem to be called LC. I'm so confused.
Yeah.
Okay, whatever. Compiler does its thing.
Yeah. So you or I'm just trying to show that it's not straightforward. That if you want to use a double precision floating point constant, you're going to have to put it into memory using the data section and then load it from memory. Here's calculating using single precision. All it's going to do is print 2π. So so there's my example of how you or I would do it. So in the data section, an assembler directive .double, and then here's the value. Now, here's something interesting. I underlined it. It's an LDR of the label. Okay. So usually you've seen, for getting at things in the data section, you've seen ADR, an LDR from a register. Okay, so this is different syntax to be able to fetch what's in memory at this label. Then I wanted to calculate 2π, so I just added double precision 0 to double precision 0, putting the result in it's cosine of 2π, back into D0. Notice BL to cosine. Now we know that when we call most functions, x0 is where the value is, the parameter, first value. Here, you see that if it's a floating point, you use the floating point registers where 0 is the first one. Okay? Any questions?
Where are the floating point registers stored compared to the regular registers? Like if I want to access the floating point registers, and then also in the same command, I also wanted to access the regular registers. So
Okay, so there are, okay, so here we are. All right. So you can use fmove to go from an X, for example, that's a 64-bit number, into a D. So let's erase the 0 here and say that's from X register to a D register. And then you can do a math operation like F mul D, I don't know, let me just put real numbers in. 0, 0, and D1. So D1 times D0, put the result in D0. So you have two banks of registers. You have all the integer registers, and you have and pointers, with pointers are integers, and then you have the float registers, and they both go from 0 to 30, 31 in this case. So Rebecca, they're just registers. They're on the CPU. They're built into the hardware of the circuitry of the CPU. Does that answer your question?
yeah, basically.
Okay, now another thing that you need to know about is there are two instructions for conversion or casting. Okay, so this did not do a cast. This fmove, that did not convert the number in XM into a floating point number. That just took the bits that were in XM and put them into DN. Okay, so if your intent is to actually do conversion of float to int into float, then you have to use these conversion instructions. And that would be something like assigned convert to float. It's in the document that we went over that had the list of all the instructions. Okay, so that's like what the mnemonic is. Close enough. You'll need to do this conversion, by the way, in a future project when we start working with floating point numbers. Class has been over 4 minutes, yet you're all still here.
That's because whatever you're talking about will probably be important and we don't want to forget it. Unless we probably die in the
All right,
future.
what have we been talking about?
Yeah, that is also accurate. I
been-
basically didn't understand any of this.
We've been talking about you, Jordan, this whole time.
I'm honored.
Don't be.
You are a floating point number.
I would happily be a floating point number.
Okay.
Imprecise and annoying.
Now, before you leave, somebody just left, right?
Yep.
Yeah, that would be, I know who that was. Now, if you're a person who did not take data structures, which is the prereq for this course, if you didn't take data structures, you may find yourselves more confused more often than people who have taken data structures. You know, pointer this and pointer that. So do let me know, and I'm willing to grant a little extra time for the people who, on projects, for the people who haven't taken data structures. Okay? All right. Okay, well, I'll see you on Thursday. Remember, Thursday is a barbecue. And good things happen to those who attend. Okay,
You're
bye-bye.
getting a better grade because you
Yep.
actually showed up.
Okay,
No,
bye-bye.
you hang up
Bye.
first.
Bye.